Hi everyone. So in this video, we'll be discussing three markers of the OMC IOQM mock. Two markers were in the previous video, and in this video, we'll do problem number 11 to 20. So let's begin with problems. So the first problem is problem 11. Uh, let's put it somewhere else. Array, where is it? Okay, let's just do this here. So basically, we have to find the number of positive integers n, which are less than 1000, such that n can be written as a plus b for some positive integers a and b, with a b congruent to modulo 5 and uh, gcd of a comma b being 1. Suppose the number of such integers is m, we have to find the sum of digits of m. So essentially, we just have to find m. So one important intuition in such type of questions is, like, eventually almost all numbers should work. Like, okay, I'll write it down. Eventually everything should work. Or a rather better way to state this is almost everything. Like, you'd expect that eventually everything except some special case would work, because you have too much freedom in this question. Like, let's say you have to form 200. Okay, 200, 201. Then basically you can choose like uh 4 plus 4. This is again. Yeah, so you can choose like 3 comma 198 or 8 comma 193, stuff like that. So there are basically like a lot of options to choose from. So you'd expect that there would be some two numbers which are co-prime in these many options. Like, there is no proof for it right now, it's just intuitively. So let's try to find numbers which work. So in general, like when you start solving the problem, you'll try with like n equals to 10, 11, 12, so on till like 30 or something, and like get intuition that what's actually going on, and then try to find some construction. So like basically I know the construction, so I won't go in like bashing out the cases and showing that. But an intuition for construction is, suppose you have to form like 201, which we discussed, and the numbers like a and b. So basically a and b should be 3 mod 5 to form something which is 1 mod 5. You can check that. Like a and b are congruent to mod 5, right? So both of them should be 3 mod 5. So the 3 mod 5 numbers which are less than 201 are 3, 8, uh, 13, so on till 200, 103, and 98, 108, so until 198. So you'll basically pick two numbers from this which sum up to 201. So what kind of numbers they can be? So like if you pick 103, the other choice should be 98. So like you can pick these two numbers. You can pick numbers which are at the same distance from here basically. Like these two numbers are at distance 1. These two numbers, okay, here it will be 93 and 108 are at distance 2, distance 3, and so on, right? So basically it's like symmetric about the center of these numbers, right? So basically, if this is n, uh, this number is, let's see, n plus 5 by 2, and this number is n minus 5 by 2. So basically, symmetric about middle of these things, essentially. So why not just see if these two numbers work? So let's see. If n is odd, n equals to 2k plus 1, then obviously n minus 5 by 2 is congruent to n plus 5 by 2 modulo 5. So this condition is satisfied. Let's talk about the GCD. So GCD of n minus 5 by 2, comma n plus 5 by 2 is GCD of n minus 5 by 2, comma uh, minus n 5. And we can write n as 2k plus 1. So this would be k minus 2 comma 5. So this GCD can either be 1 or 5. So the GCD k minus 2 comma 5 equals to 5 implies k is congruent to 2 mod 5, which implies n is congruent to 0 mod 5. So let's leave the n equals to 0 mod 5 case at the side for now. N equals to 0 mod 5. So apart from n being 0 mod 5, the GCD will be 1 of these two numbers. These things will be 1. So basically, any odd number for any odd n, pick a comma b equals to n minus 5 by 2 comma n plus 5 by 2. And this would work. An odd n which is not 0 mod 5. This would just literally work for you. So now you'll think about what to do in even n, right? So in odd n, we try to take the things which are at the center. Let's try to do the same thing for even n. So even n. In this case, the two numbers which will be at like around the center will be n by 2 minus 5 and n by 2 plus 5. In this case, let's see. So obviously they're congruent modulo 5. So let's take GCD. Array, what am I doing? Add these numbers at the just a second. So 100, 100. Let's do 102. So for this it will be 46 and 51. Uh sorry, 56. Or there would be 15. Yeah, yeah, these two will be at about the center, I believe. Yeah, you can check that. So, oh, okay, like you can just take n by 2 comma n by 2 as well. But in that case, like the GCD will be, what do you say, not equals to 1, right? So you do not consider that case. So GCD of 2 minus 5 and n by 2 plus 5. This is equals to GCD of n by 2 minus 5, comma, 10. So, wait, is that 10? Yeah. So we can take n equals to 2k. So this is GCD of k minus 5, comma 10. So clearly, if k not equals to 0, k should not, okay. So this GCD can be 1, 2, 5 or 10. Let's see when the GCD is 5. This means 5 divides k minus 5, which implies k is 0 mod 5, which implies n is 0 mod 5, because n is just 2k. So it is just this case, which we put at side for now, right? So let's just ignore when 5 divides k minus 5 case. That is n equals to 0 mod 5 case. So now the GCD can only be 1 or 2. And for GCD being equals to 2, k must be odd. So this is an issue. So let's take things which are like, so basically you're taking this, right? So you have 2k. You consider k, like these are the numbers which you'll consider for the sum. K minus 5. So we saw that this does not work. This does not work for odd k. Let's try these two numbers now. So GCD of k minus 10, comma k plus 10. This would be GCD of k minus 10, comma 20. So since we are not taking k as 0 mod 5, this GCD can only be 1, 2 or 4. But notice that k must be odd. So for odd, k minus 10 will be odd. So the GCD will be 1 if this is not 1. So basically, at least one of these two will have GCD 1, which means for even n, either n by 2 minus 5 comma n by 2 plus 5 works, or n by 2 minus 10 comma n by 2 plus 10. One of these two should work. So basically we have characterized all n which would work except n equals to 0 mod 5. For 0 mod 5, the thing is, so, okay, A and B are congruent modulo 5. A plus B is congruent to 2A mod 5, which should be congruent to N, which is congruent to 0 mod 5, right? Because A plus B is equals to N, right? Which implies A is congruent to 0 mod 5, which means A and B are both 0 mod 5. This implies GCD of A comma B is at least 5, which is not 1, right? So no number which is 0 mod 5 works. But see, this is not the complete answer. We miss some edge cases. Like in the odd n case, if you have to pick n minus 5 by 2, n minus 5 by 2 must be greater than 0, right? Because A and B can only be positive integers. See? So this means for this thing, n should be greater than 5. So we have to check 1, 2, and 3, 1, 2, 3, 4 manually, basically. Similarly, in the even case, this thing and this thing should be greater than 0. This gives a stronger bound, which is like uh, n should be greater than 20. So basically, you have to check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, array, so until 20 manually. But this is not big work, right? It's just 20 numbers. And like if you do it smartly, it should not take you more than like, I believe, 1 minute, which is, I think, a fair deal for a 3 marker question. The check part I'm saying. Okay, I'll not show the calculations right now, but I have written down in my notes that which numbers do not work. It is 1, 3, 4, 6, 1, 3, 4, 6, 8, 14. And all 0 mod 5 numbers. So the number of numbers which work comes out to be 794. You can calculate that. I'll not doing like basic computation here. So M is 794 and we have to find sum of digits. So sum of digits will be 20. So the answer to this problem is 20. Okay, I'll write it in a better way. Problem 11, 20. Let's move on to problem 12. Problem 12 is a nice problem. It's like based on a particular idea. So if you have seen that, this problem would be like easier for you. So see, you have to basically find the two largest prime which divide this huge number. Obviously, they will not expect you to calculate seventh power of something. So there must be some clever thing. And since you have to find the two largest primes, it just means that you have to find what do you say? Like the whole prime factorization. I don't think there's a nice way to find the largest prime dividing directly. Okay. So what is the one basic thing? Like this is given you in terms of like 1, 2, 9, 7 to the power 4. So let's just write this in terms of prime factors. So this would be like 2 to the power 14 times 3 to the power 8. And you can write this as basically, see, it is something like, and we can write this as, how do I motivate this? Basically, it's like a to the power 4 here, and you have some factor of 2, 2 times some b to the power something. 2 to the power something times b to the power something. Like this just looks like Sophie German. I think the idea is like if you have seen Sophie German before, then it's like easier for you to spot. Otherwise, it's slightly hard to like spot that factorization. So I'll show you how this thing works. I think it's a good enough trick to remember for IOQM. So basically, we try to factorize a to the power 4 plus 4b to the power 4. This can be written as a square plus 2b squared whole squared minus 2a square b square whole squared. Is this it? Yeah. And then you can write a square minus b square. So it becomes a square plus 2b square minus 2a square b square times plus this thing here. So it's just like a nice way to factorize stuff. Okay, so let's see. 1297 to the power 4 plus 4 times 2 to the power 12 times 3 to the power 8, which is 1297 to the power 4 plus 4 times 2 to the power 3 into 3 square to the power 4. So this would become 1297 squared plus twice of 2 to the power 3 times 3 to the power 2 squared minus 2. Wait a second. A square plus A4 plus 4B4 plus 4 square B square. Okay, so yeah, so this would be minus twice of 1297 squared times B squared. 2 to the power 3 times 3 square squared. And we'll write the plus term later. Let's just see this term, the plus term. Uh, let's see. Okay, you can write this thing as twice of mm, wait. Okay, you can write this as 2 to the power 7 times 3 to the power 4. And I think I messed it up slightly now. I see. Yeah, it shouldn't be this here. Like this should be more factorizable. Yeah, okay. I should write it down clearly. So the thing is, it's like 8 to the power 4 plus 4b to the power 4 plus uh 4a square b square minus 4a square b square. So this thing is a square plus 2b squared whole squared minus 2ab whole squared. Yeah, there shouldn't be like a square here. I messed up that part. So this would be a square plus 2b square minus 2ab times a square plus 2b square plus 2ab. And you can go down further if you need. Like this would become a minus b whole square plus b square times a plus b whole square plus b squared. Cool. So let's try to apply the same thing here. So here it would be this thing. And I can write this thing as 1297 minus um 2 cube times 3 squared whole square plus 2 cube times 3 squared. This would be 2 cube is 8 times 9 72. So minus 72 it would be 1225 squared plus uh did I mess up again? I don't think so. Plus 2 times. Oh, yeah, there's a square here. Okay, I'm making so many silly mistakes. Uh, yeah, there should be a square here. Like it's basically, I write this as 2 cube times 3 squared whole square plus 2 cube times 3 squared whole square. And I take this, and this. So like a square plus b square minus 2ab to form this. And I take the remaining term here. So it should be a square here. So this would be 2 to the power 6 times 3 to the power 4, which is uh and I can write 1225 as 45 squared. Sorry, 45, no, 35 squared. 35 to the power 4 plus 4 times uh this would be 6 to the power 4. So yeah, Sophie German again. Yeah, slightly annoying, but it just works out. Like the numbers are so nice. So this is now a squared plus b squared plus 2ab and a squared plus b squared minus 2ab. Okay, it's twice here and twice here. Huh. Or I can just write this as, yep. So this would be 41 squared plus 6 squared. And this would be 40, no, not 41, but 29 squared minus, no, plus x squared again. 35, yep. And similarly, let's check out the other term. So after you do the stuff here, you'll get like 1297 plus 2 cube times 3 squared whole square plus 2 cube times 3 squared whole squared, which would be, so 1297 plus this is 72. This is 1368 square plus 4 times 6 to the power 4. And 1368 is, I think, wait, no, did I mess up the, yeah, it's 1369. Yeah, 1369. This is uh 3 and 16. I think this is a perfect square. This should be, I think it should be 37. Let's see, 37 into 37. So 21 to 59, 111. Yep. So this is 37 square. So this is 37 to the power 4 plus 4 times 6 to the power 4, which becomes eventually uh a plus b 43 squared plus 6 squared times 43 squared minus 6 squared. Sorry, 31 squared plus 6 squared. Like, I'm writing this directly by using this thing basically. One second, I'll tell you. This thing here. If you do not trust this, like, you can do this every time, like all these steps, like these steps, and eventually come here. So the whole thing basically, which was, I just forgot the question, 1297 to the power 4 plus uh 3 times 12 to the power 7 is 29 square plus 6 square times 31 square plus 6 square times 41 square plus 6 square times 43 square plus 6 square. Now the point of this is all of these are small numbers. Like this is something like 3 digit. This is also 9, 3 digit, I think, like almost 4 digit. And these two are 4 digits. So like to find the prime factors of these four numbers shouldn't be like a hard deal. Okay. And I'll not do the calculation in this, but I have calculated them before. And the two largest prime numbers that will get is 997 and 877. So the difference of these two is 120. And wait, what are we supposed to find? Find the sum of digits. So the sum of digits is 3. So the answer is 03. Sorry, I slightly messed up the explanation of that problem. But the main idea was to like spot the Sophie German. Like you see a to the power 4 and this becomes like b to the power 4, some constant which is 4. So you just see, oh, it's Sophie German. And I think like this form of Sophie German is like highly useful. So once you write in this form, you see, oh, you can apply Sophie German again, which reduces this even more. And then it's just bashing out the prime factors. Okay, think that this is a misplaced problem. It should be a 5 marker rather. Like there it will make more sense because you have to do so many calculations as well. So it consumes time. So probably it would have been better if we have given it 5 marks. But okay, whatever. Next problem. Okay, this is going to be a long problem, I believe. Problem 13. Determine the sum of all positive integer n such that this thing is a perfect square. This is another type of question in which you just have to trust that the most basic thing would work, like the most obvious thing that you would try, it would eventually work. Like it's just about like having trust in that thing. So what's the most obvious thing? Like you do this equals to a square minus 1 for some a. So this is a minus 1 times a plus 1. Now notice that both of these have same parity, right? Same parity. And okay, let's just assume that n is greater than 1 for now. N equals to 1 case we can just check later on our own. So Like this thing is even. So if a minus 1 is odd, then this is odd. So odd times odd cannot be even, which means that a minus 1 comma a plus 1 are both even. So we can let a minus 1 as 2 to the power p times s and a plus 1 as 2 to the power q times s. So like this is sort of a well-known fact, or like I think you should know this with enough practice that uh 4 cannot divide both a minus 1 and a plus 1. So the reason for this is, suppose 4 divides a minus 1 comma a plus 1. This implies 4 divides their sum. Okay, let's take difference a minus 1 minus a minus 1, which implies 4 divides minus 2, which implies 4 is less than equals to 2, which is contradiction. Which means uh P or Q cannot be both greater than 2. This is not true. Also notice that product of these two things is like this. So this gives you P plus Q should be n minus 1. Oh, sorry. Here it should be R, like just some another variable. And R times S would be equals to N. So you have these conditions. Okay, we got P and Q cannot be both greater than 2. So this means that, and also P and Q cannot be, either of them cannot be 0, because we are assuming they're even. So if there's, oh, S and R are odd, I should have specified that. So yeah, P and Q cannot be 0, which means that you just have to deal with two cases. Case 1, P equals to 1. In this case, Q would be equals to, like Q plus P is n minus 1. So Q would be equals to n minus 2. This implies a plus 1, which is 2 to the power q times r, is equals to 2 to the power n minus 2 times r. So see, one thing about such kind of problems is like when you have some conditions, you'd want to like, I think this is like a very obvious idea which is used in such problems, like try to find bounds on n. Like bounds is basically like some sort of conditions on n. So it's fine even if the bounds that you find are weak. Like if you find a weakest bound, you can probably improve on that later. But finding just some sort of bound should be good for you. So see, here you have details about P and Q, but you do not know much about R and S. So you try to avoid R and S as much as you can when you're trying to find bound. So like I have this thing. So the weakest bound would be like this thing is just greater than or equals to 2 to the power n minus 2. And this implies a minus 1 is greater than or equals to 2 to the power n minus 2 minus 2. So now a plus 1 times a minus 1 is greater than or equals to 2 to the power n minus 2 times 2 to the power n minus 2 minus 2. And this thing is equals to a square minus 1. And a square minus 1 from here is n times 2 to the power n minus 1. So this implies n times 2 to the power n minus 1 is greater than or equals to 2 to the power n minus 1 times 2 to the power n minus 3 minus 1. Which means n is greater than or equals to 2 to the power n minus 3 minus 1. So we get this from case 1. Let's see case 2. Q equals to 1. Also, one thing, once you get this condition, just notice that how strong this condition is. Like here you have a linear function, but here you have an exponential thing. So like n would be like, you'll expect that after n greater than or equals to 10, definitely this will be bigger. So yeah, it just like narrows down your conditions a lot. Okay, let's take the other case, q equals to 1. In this case, you'll get p equals to n minus 2. Yeah. And this means a minus 1, which is equals to 2 to the power n minus 2 times s, 2 to the power p times s, right? So p is n minus 2 is greater than or equal to 2 to the power n minus 2. And this implies a plus 1 is greater than or equals to 2 to the power n minus 2 plus 2. So the product of a minus 1 and a plus 1, which is n times 2 to the power n minus 1, would be greater than or equals to 2 to the power n minus 2 times 2 to the power n minus 2 plus 2, which implies n would be greater than equals to 2 to the power n minus 3 plus 1. And come on, this is the equation of the similar format which we obtained in case 1, right? These two are very strong conditions. Like this is stronger than this thing. So you just go with this case. And like this is a very strong condition. Uh like okay, let's see n equals to 1. 1 greater than equals to wait a second. Okay, yeah, so 1 is greater than equals to 1 plus 2 to the power minus 2, which is true. N equals to 2. 2 is greater than equals to 2 to the power minus 1. Wait, just a second. Yeah. So which is false. For n equals to, sorry, this is true, and yeah, this is also true. For n equals to 3, 3 should be greater than equals to 1 plus 1, which is true. For n equals to 4, 4 should be greater than equals to 2 plus 1, which is again true. For n equals to 5, this would be 5 greater than equals to 5, which is true. But for n equals to 6, uh, 6 greater than equals to 9, which is false. And by induction, you can show that any n greater than equals to 6 will not satisfy this. So for the problem to be true, one of these cases must hold. Like, like this, for the problem to be true, this thing must be true, which is only possible if n is 1 to 5. So we can just check these cases manually. Like, come on, these are just 5 cases, right? And for one, this would like essentially just n equals to 5 works. I'm pretty sure. So that is the only solution. Like you can check those 5 cases manually. So the sum of all such positive integers, like sum of 5 is just 5. Okay, a very weird way of saying it, but anyways. So the answer to this question is 5. Okay, I think apart from these, all the 3 markers were relatively easier. So we can just quickly do those. Let's move on to question 14. A 30 centimeter long wire is bent to form a triangle such that it has the greatest possible area. Okay, so this should be like, I think, intuitive by symmetry. Like basically, the problem is saying find the triangle such that, oh, horrible handwriting. Perimeter is fixed while the area is maximum. By symmetry, like you'd think that such a triangle should be equilateral. Okay, but this is just intuition. Let's do it formally. So suppose you have ABC as a triangle. Also, this intuition, like I think you should have to like guess in IOQM. Like, what if you have less time? You should go by like symmetry. Like symmetry works in a lot of geometry problems, like at least problems of this flavor. Okay. So ABC, and let's say the sides are C, A, B, and A plus B plus C is fixed, and we have to maximize the area. So what would be area by Heron's formula? Under root. I'll take out the by 2's common. So A plus B plus C times A plus B minus C, A minus B plus C, minus A plus B plus C. So you have to maximize the area, which means you have to maximize this thing. If we apply AMGM, let's see, C cancels out what equal to C. Okay. So A plus B plus C plus A plus B minus C plus A minus B plus C plus minus A plus B plus C. By the way, notice that all the four terms will be like greater than 0, like positive by that thing. Triangle inequality. 4 times fourth root of a plus b plus c, a plus b minus c, a minus b plus c, minus a plus b plus c. And this is what we have to maximize, right? Like this would be the maximum value. And the maximum value is, I don't think the maximum value really matters. Like this is the maximum, we know that. But the important part is, when is this maximum achieved? Uh, okay, I think the better thing to do here is, this is kind of not good, because like this maximum is achieved when a plus b minus c is, yeah, I have to go for a bit. So in this case, like the equality is that like a plus b minus c equals to a plus b plus c and so on other things. But this is if just c equals to 0, which is not helpful. So like the thing is, like this thing is a constant, right? The perimeter is fixed. This is the perimeter. So it's not useful to consider this term. Like this term is fixed. Like the area is basically dependent on this thing. So if you apply AMGM on that thing, you will get, would be greater than equals to 3 cube root of, uh this is p minus 2a, p minus 2b. I'm lazy to write all that, so I'll just write this. And this is the maximum value. But the point is, when is this maximum value attained? When a plus b minus c equals to a minus b plus c equals to minus a plus b plus c. So this thing would give you b equals to c equals to a, which means the triangle is equilateral. As we wanted it, like by intuition also this was true, right? So in equilateral, like the total perimeter is 30. So each of the sides will be of length 10. 10, 10, 10. Let's say this is the altitude, h. So half base into height should be equals to area, which is root 3 by 4 a square, unless I'm wrong. So h is 5 root 3. It just says like m be the mean of length of all three altitudes. So all the three altitudes are of equal length. So the mean is just this. So m is 5 root 3. And we have to find m square. So it's just 75. So the answer is 75. So in this case, I think intuition of having that the triangle is equilateral is important. Like that gives you some direction to go with. Like basically symmetry, intuition of symmetry, I would say it rather. Moreover, like, see, calculating the length of all three altitudes just sounds tiring, and they would not want you to do that, like such calculations. I assume so, most probably. So there's probably some sort of scam involved, I would say. So identifying that is a good part. Okay, let's move on to the next question. This was a basic algebra question. Uh, okay, so x square. Hmm. So to add, so as to motivate this, we see that it's under root of this term, under root of this term, under root of this term. But how do you relate that? Like if you have to go back from here to here, one way is to square this. But that gives you some terms like x root xy, y root xy, which is not really like helpful, right? Another way which you would have seen in like I think complex numbers usually, like whenever you have to go in that form, you try to multiply it by this thing, like the conjugate. This is not really the conjugate, but I think the intuition behind it comes from that thing. So this thing would be x square plus y square plus 2xy minus xy, which is just that. So I can write this thing as this, which means 19 times x plus y minus root xy is equals to 133. 763, which means that x plus y minus root xy is 7. And now, is it 7? Yeah. X plus y plus root xy is 19. So this gives you x plus y as 13. 13, right? Yeah. And root xy as 6, which implies xy is 36. So y is 36 by x plus 36 by x is 13, x square minus 13x, plus 36 must be 0. What do we have to find? We have to find x plus 9. So the roots are x equals to 4 comma 9, which gives y as 9 comma 4. So x plus y is 13 in both the cases. Maximum value of the sum, there's only one value, 13. So the answer should be 13. So I think in this problem, like there was not much to like motivate, but just like how do you use these two terms together? Like how do you go from here to here? That is, I think, the most important part. Okay, I'll create a new page. Uh, like this. Oops. Yeah. Three marker. Huh. So next problem, problem number 16. Okay, this is a long problem. I'll not read out the whole problem. So you can read out the problem and then I'll explain the solution. Okay, so I'll give a quick, brief description of the problem instead of like letting you read it itself. So basically, like world is divided into two creatures, vampire and werewolves. Vampires lie about werewolves, whereas they say truth while talking about a vampire. And this thing is always true. And so do werewolves. Like werewolves talk false about vampires, but talk true about werewolves. And this statement just means that vampires know which person is a vampire and which person is a werewolf. So basically, everyone knows that who is a vampire and werewolf. And statement like this, that X is a vampire, is a statement about X, not a vampire. Okay. So now what we are given is there are some number of creatures who are sitting around a circular table, and everyone says, you lie about your right hand neighbor. So basically, let's say there are three people, P1, P2, P3. P1 says to P2, like to their right hand neighbor, P1 says to P2, P2 lies about P3. So this statement is about P2. Okay. So we have to find what can be the possible values of n. So let's just do the most basic thing. Like what happens once you have like, let's say P1 in this scenario, P1 is a vampire and P2 is a werewolf. So basically the setting is like vampire, werewolf. What will be the next thing? So P1 says P2. Okay, see, this statement is about P2 said by P1. So a vampire is saying a statement about a werewolf, which means that this statement will be false, which means that the statement that P2, which is a werewolf lies about lies about P3, this is P3, is false, which implies werewolf says truth about P3. This implies P3 should be a werewolf. So basically, if you have a vampire werewolf, then the next person will be a werewolf. And let's see what happens when we have a vampire. Then P1, P2. So vampire lies about P3. This statement is about this person said by this person. So vampire is saying a statement about vampire, which means it should be true. Which means that V lies about P3. A vampire lies about P3, which means P3 should be a werewolf. So we should have like VWW or VVW. And similarly, we should have WWV or WVV. So we can basically like combine all of these things and we can say if we have like somewhere, like, okay, uh, let's see, n is greater than equals to 2, right? So suppose you have vampire, then the next version should be a werewolf. And from VW, the next should be a werewolf. The next can be a vampire. So you can make this a circle. Like this can be a possible circle. Vampire, werewolf. And yeah. So vampire, werewolf followed by werewolf, werewolf followed by vampire, vampire followed by vampire, and so on. Continues. So this is a possible thing. So n should be equals to 4. Or uh, we can have, okay, so VVWW. Suppose instead of taking this vampire as the next vampire, we can write the V again. And then WV should be V, VV should be W, VW should be W. And then the next vampire can be this. So in total, you'll get that 4 should divide N. So the possible number of creatures is 4, 8, 16, so on till um, N less than equals to 100. So now, what are we asked? S be the sum of all possible values of N. So S will be uh, N by 2 into A plus L, which is 104. So it is 52, which would be 5200 divided by 4, 2600, 1300. So S is 1300. We have to find sum of digits of S, which is 4. So the answer to this problem, 16, is 4. So this problem was like, I think, on the easier side of a 3 marker. Like, you just have to do, like, what if there's a vampire werewolf or a vampire, and then see what the next creature would be. And then it just like follows. Like, you just find nice patterns and then you try to like uh accumulate all the things that you get. Cool. So let's move on to the next problem. Problem number 17. This problem was a nice problem. Like when I was trying this problem, I was trying it with another person and it took a lot of time. So see, one thing to try here is like this looks like cosine rule, right? Like you can write stuff like a square by 2 plus a square by 2 plus b square plus b square by 2 plus c square by 2 minus ac minus root 3 bc minus 0 ca equals to 0. And then you can club this like a square by 2 minus ac plus c square by 2 and for other terms also. But the issue here is if you see this 1 by 2 times a square plus c square minus 2ac. This implies cosine of angle B must be minus 2. Oh, wait, shouldn't be minus 2. Uh, yeah, like minus 2 plus 2. I'm forgetting if this is like minus or a plus in cosine rule. I think it's a minus. So, like, cosine of angle B is plus 2. Or minus 2, but never mind. That's just like a sign issue. Does not matter. But this is not possible. So, you cannot really do this, which is sad. What other thing can you do? Another thing which you can do is like there's a squares and like terms which are like sums of products of two terms. So the next intuitive thing is I think completing the square, and that just magically works. I think like the only motivation is like cosine rule does not work. You have squares and like products of terms like product with two terms. So all these terms occur in like a plus b square and stuff. So just try to complete the square. Okay, so if we try to complete the square, this would be, let's see. So a square plus b square plus c square minus ac minus root 3 bc equals to 0. So let's see how we can write this. So a square minus ac plus c square by 4 plus 3c square by 4 c by 2, yeah, plus b square minus root 3 bc equals to 0. And this thing is a minus c by 2 whole squared. And this thing I think is root 3c by 2 minus b whole squared. Let's see, 3c square by 4 plus b square minus, yeah, equals to 0. Which means a equals to c by 2 and b equals to root 3c by 2. So the sides are like in triangle ABC, root 3c by 2, and then this is c by 2, and this is c. You can scale if you want, like multiply by 2 every side, because even if you scale, the angle will remain same, right? Like you can do this. Define this as b dash, c dash. Then this is c. This is root 3c. The angles are same. Like this is angle C, angle C. Angle A is same. Angle B is same. and this is 2c. And clearly this is a Pythagorean triple. So like c square plus root 3c squared equals to 2c whole squared, which means that this angle is 90 degrees. 90. And you can take cosine of angle C as root 3c upon 2c, which is root 3 by 2, which implies C is 30 degrees. So 30 degrees and this is 60 degrees. What do we have to find? C minus B plus A. I just wanted to like make the answer subtraction look slightly scarier and not just directly. So this is 30 minus 60 plus 90, which is 60. I could have just asked like angle B. The answer would be same. It does not matter. So the answer is 60. The main idea was like completing the square. Like you just have to see that, oh, this looks like square terms. So yeah. Okay. Problem 18. So you have ABCD is a square. ABCD. Points K and L are taken on BC and CD so that angle AKB equals to angle AKL. We have to find angle KAL. Okay. So basically, if we see KA is external angle bisector of angle BKL. Now, once you put it this way, like try to see KA as this way, I think it's more intuitive to define like see other angle bisections. And then you see this most natural angle bisection in a square. This angle is bisected, like diagonal bisects the angle, right? And this does give like so A is intersection of internal angle bisector of angle KLC and external angle bisector of LKC. Oh, external angle bisector of LKC, CK, not BKL. So you just see that the oh, this is the intersection of two angle bisectors, one internal and one external. So A is X center of triangle KCL, which means angle KAL is 90 minus angle KCL by 2. KCL is 90. So this is 90 minus 90 by 2, which is 45 degrees. So yeah, like I think it's just like observing that, oh, A is the eccentric and this works out. And to observe that the motivation is like it lies in one of the angle bisectors. Are there any other angle bisections? Because square is a lot symmetric. So yeah. So the angle is 45. This was a quick problem. Maybe it should be a 2 marker rather, now that I think of it. So yeah. Okay, 19th is like a highly computationalist problem, like maybe J mains style, I would say. So you have triangle ABC. Oh, angle A is 90. Uh, I is the in center basically. IH perpendicular to BC. H is the in touch point. We are given that this is 5 centimeter and this is 8 centimeter. Find the area, which is basically like finding base and height. Okay, very naive terms, but find AB and AC. Okay, a naive thing that you do in this case is like, oh, this is 13, and you know that 5, 12, 13 is a right angle triangle. So just take 5 and 12, and the area is 1 by 2, 5 into 12, 30. I think like if you are not able to solve this, it is a good enough guess. Unfortunately, the answer is incorrect, but I don't think you could have guessed better in this problem. Okay, so let's see the solution. So see, like you know that this is the in touch point, H. And I think that you should know by this point, but like BH is a nice length. BH, CH are nice lengths. Okay, I do not know who uses H for in touch points, but whatever. So H is here in touch point. Do not confuse it with orthocenter. BHCH are nice lengths, and they are like just given to you directly, right? So let's try to use them. Okay, how to find BH? See, if we draw the N circle, let's say this length is X. Since these two are tangents from the same point, this length should also be X. Uh, and CH and this point are also tangents from the same point. So if this length is Y, this length is also Y. And these two lengths will also be by similar logic Z and Z. So now if you sum all these lengths, X plus Y plus Z, it will be twice. And this should be equals to perimeter. So X plus Y plus Z is basically semi-perimeter. So X is, okay, let's just say it perimeter by 2. P by 2 minus Y minus Z, right? What is Y minus Y minus Z? Uh, so Y plus Z is AC, which is B. So X is S minus B. So basically, this length is S minus B. This length comes out to be S minus C, S minus C, S minus A, S minus A, S minus B. So basically, like all the lengths related to in circle are nice. That is the intuition. So now you have S minus B is 5, S minus C is 8, and you also get that uh this length is like C and this length is B. So B square plus C square is 13 squared by Pythagoras. Let's see what does this give you. This would give you A plus B minus C equals to 16. And this thing would give you A plus C minus B equals to 10. So if we sum both of this, we get A equals to 13. Okay, not useful, but put it back in here, you get B minus C is 3. Now you have that B square plus C square is something, right? So let's square this. B square plus C square minus 2BC is 9. B square plus C square is 169. So this equals to 2BC. So BC comes out to be 80. So C equals to 80 by B. So B minus 80 by B equals to 3. So B square minus 3B minus 80 is 0. So B is, this is just like quadratic formula. B square minus 4 is 329 over 2. So basically like this just means that B comma C are 3 plus root 329 by 2 comma 3 minus root 329 by 2 or the other way around. But that does not really matter. Okay. Like B should be 3 plus C. So does this look like 3 plus C? Oh, oops. Sorry. Okay. No, we don't do this way. Ignore that part. So B is like this thing. Clearly B cannot be negative. Yeah, I was giving wrong explanation. Like if you take minus that, this thing would be negative, right? So B is the positive thing. 3 plus 329 by 2. And from here, B minus equals to 3, you get C is root 329 minus 3 by 2. And now area of right angle triangle is half BC. So half 3 plus root 329 by 2, root 329 minus 3 by 2. And this becomes 1 by 8, excuse me, into 329 minus 9. So 1 by 8 into 320, which is 40. So naively, you would have guessed answer as 30, but I don't think you can guess better. So I think that is like decent if you're guessing, but this is the correct solution. And I think this is like a simple problem once you know this thing. So 19 is 40. Oh, code block stuff. 19 is 40. Answer to problem 19 is 40. Okay. Problem 20. Okay, so in this problem, basically like the statement is sort of complicated, but the idea of the problem is pretty simple. So I'll just explain the statement. It says that phi is a function in which if you input a set, let's say any set, 1, 2, 3, 4, 5, 10, 12, 18, doesn't matter. It will just output you all the even index numbers in the set. So like this is at index 1, index 2, 3, 4, 5, 6, 7, 8. So even index numbers will be 2, 4, 10, and 18. So it will output you this set. And if you input an empty set, like the empty set, it will output you the empty set again. So that is the crux of the problem. And then it just asks you to do computation. So let's see. So you have to find like phi of k is defined as like phi k of some set is basically phi applied k times, like compositional k times. Okay, so you have to find of the largest n such that these two things are equal. Also, a small typo should be like large brackets here, but I don't think like you'll give bonus for that small thing. Doesn't matter. Like, I think this should be obvious at this point. Okay, so let's see how phi function works. Like the you see that set is like 1 to n always, right? So let's see phi of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So once you apply the first time you'll get 2, 4, 6, 8, 10, 12. The second time you'll get even indexed here 4, 8, 12. Third time you'll get 8. See, the thing is every time you're taking the even index numbers, right? Like here the index are 2, 4, 6, 8, 10, 12. Here the index are 4, 8, 12, so on. Here the indices are 8, 16, 24, and so on. Like we only started with 12 numbers, so 16 is not here. But in the next case, the indices will be 16, 32, and so on. So basically, we can see that uh, the indices here are all multiples of 2. Indices here are all multiples of 4. Here they are multiples of 8 and 16. Formally writing, it will be phi of k to the sum set n is the set of all elements x such that v2 of x is greater than equals to k and x is in the range 1 to n. This is how we will formally define the set. Like the idea is just like the maximum power of 2 dividing x should be greater than equals to k in the kth step. That is all. So let's see what this would be. 2 to the power 10 is, let's see, 2, 4, 8, 16, 32, 64, 128, 256, 500, 1024. So all the multiples of 1024 will be there. 1024 is there. And 2048 cannot be there because 2048 is greater than 2023. So that cannot be there. So it is just 1024. Now, if we take n as, let's say, 2048, then obviously you will get 2048 in the output, 1024 and 2048. So these two sets won't be equal. But for anything less than 2048, like let's say 2047, the output will be 1024 only because 2048 is greater than 2047. So this is the maximum number, right? Like for 2047 it works, but for 2048 it does not work. So this is maximum. So n is 2047. And we have to find sums of squares of digit of n. So it's 2 square plus 4 square plus 49 square, which is 4 plus 16 plus, oh sorry, 7 squared, not 49 squared, plus 49. And this is 69. So the answer to problem 20 is 69. So these were all the solutions for all the three markers. Like I think most of them were not that hard, except like problem 3, I believe. But in most of the question, it was like you just do the basic thing possible, and it eventually works out. Like no fancy theory was used in any of the problems. So yeah, in IOQM you can expect that only. So in next we will probably discuss all the 5 marker solutions, or maybe I'll divide it into two parts. And like first, like 21 to 25 in the first video, and 26 to 30 in the next video. Okay, so I'll stop recording.